Hello, everybody. This is Drive Me to Your Leader with Mr. Red, and in this podcast, we hope to bring to you discussion, argument, and maybe just some fun on the way through. Today, it's just a 30-minute bonus episode, and I'm going to be doing it on radiation, maybe with a bit of nuclear power on the end. And I'm hoping to fit it all in about 30 minutes, but I think that's an incredibly ambitious time scale. You may or may not be able to hear that I've upgraded some equipment, so it might sound just a little bit better, but maybe you'll be the judge of that. Let's go straight into it. I wanted to do radiation for a little while. I haven't really been able to find anyone to talk to or talk with who's also, I would say, knowledgeable about the topic, but also wants to talk about the topic as well. I want to talk about it because I think it's a very misunderstood topic, and I think it imbues a fear in people that isn't always altogether deserved, actually. So maybe we can dispel a few things about it today and learn a few things in unexpected areas, actually. We'll see how far we can get into this today. I just want to start with the different types of ionizing radiation. And essentially what ionizing radiation means is that it's the stuff that's going to cause you to cancer. It's the stuff that's ultimately going to kill you. But I'm going to get into it. And it doesn't always, by the way, but we'll get into it. So there's about 5 types of ionizing radiation, but we're going to do 3 mainly because the other 2 aren't altogether, well, you'll see. So alpha radiation, if I can just explain it, alpha radiation occurs when an atom undergoes radioactive decay, giving off a particle called an alpha particle, consisting of 2 protons and 2 neutrons. Oh, you know what? Before we begin, actually, for those of you who aren't aware, basically, I have to explain this bit. Each thing in life is an element. So whether it be iron, whether it be oxygen, whether it be nitrogen, it's all an element. And those elements are mainly, most of the weight is protons. And that gives each element an atomic weight. So with oxygen, it has 8 protons, so it has an atomic weight of 8. You don't necessarily need to get too much into it, but then you also have neutrons that make a very minuscule amount of the weight, but they produce an isotope. So if you have oxygen 8, you have a stable oxygen element because it has the right number of neutrons than it needs. However, if you then have something like oxygen 10, or I don't know the radioactive side of, but essentially, if it has too little or too much of something, usually neutrons, but it can be electrons too, it usually becomes ionizing, and that's the stuff that produces these kinds of radiation when it either gets too heavy and it needs to shed something, or it becomes unstable in a certain way, and it keeps going till it gets to the point it wants to come to. So alpha radiation occurs when an atom undergoes radioactive decay, giving off a particle consisting of 2 protons and 2 neutrons, essentially the nucleus of a helium-4 atom, changing the originating atom to one of an element of an atomic number 2 less and atomic weight 4 less than it started with. Sorry, an atomic number is protons. I got that a little bit mixed up there. So, due to their charge and mass, alpha particles interact strongly with matter and only travel a few centimeters in the air. Alpha particles are unable to penetrate the outer layer of dead skin cells, but are capable, if an outer-emitting substance is ingested in food or air, of causing serious cell damage. So, alpha radiation essentially won't be able to pierce anything. It can't even pierce a piece of paper. But if you ingest it or get it into your bloodstream in some way, it's often fatal because you don't need a large amount of it. And actually, it was used as a poison to assassinate someone, but we'll get more into that in a little bit because there's a bit more to that. The next is beta radiation. Beta radiation takes the form of either an electron or a positron, a particle with the size and mass of an electron but with a positive charge, being emitted from an atom. Due to the smaller mass, it is able to travel further in the air up to a few meters and can be stopped by a thick piece of plastic or even a stack of paper. It can penetrate skin a few centimeters, posing somewhat of an external health risk. However, the main threat is still primarily from internal emission and ingested material. So it's kind of your middle ground. It's going to travel a little way, and it will penetrate to some degree, but it's not going to penetrate your whole body. And so it's kind of like a half and half. And then we get onto our next one, which is gamma radiation, which is, unlike alpha or beta, does not consist of any particles, instead consisting of a photon of energy being emitted from an unstable nucleus. Having no mass or charge, gamma radiation can travel much further than through the air than alpha or beta, losing on average half of its energy for every 500 feet. Gamma waves can be stopped by a thick or dense enough layer, usually lead, with high atomic number materials such as lead or depleted uranium being the most effective form of shielding. That's why if you ever watch the Chernobyl documentary and the liquidators, when they go up on the roof and they have to clear all the radioactive graphite from the roof because the robots can't do it, they've got those lead uniforms because it literally probably did save quite a few of their lives doing that. And gamma radiation is usually the stuff that most people get scared about, for good reason, because it's that stuff that's really going to go a long way and it can penetrate you. And you don't need to eat it, you don't need to do anything. You just have to be in the wrong place at the wrong time. If you have an exposed nuclear reactor, obviously, but that's the kind of thing that people generally get quite worried about. There's two other types of radiation. One's X-rays, but I think people tend to know how they work because of the medical reasons. I could get into the technically how they work, but I don't think it's that necessary because it's not what we're going to be focused on today. There's also neutron radiation, which is essentially when a neutron escapes and it will just shatter straight into your body. And that's probably I would say it's probably the most powerful type of radiation, ionizing radiation, but it's incredibly rare. And the only instance, I'm not saying it's the only instance ever, the only instance I've ever heard of it happening is Chernobyl, when we had a open nuclear reactor and it was still pouring out fission products. That's the only time I've ever known neutron radiation. Whether there's other times it's happened, you tell me, because I'm not 100% sure on that. But it's very rare, so we're not really going to be focusing on that either. So those are the types of radiation, and people get very scared of radiation, but actually the data on it is actually hard to come by because we have the Chernobyl data, but the only real data we have of it harming human beings beyond that is the 2 atomic bombs in Nagasaki and Hiroshima. And a lot of radiation data and understanding of how it affects human beings comes from those 2 instances. And so I want to pick up on, there's a book called Radiation, What It Is and What You Need to Know by Robert Peter Gale, MD, and Eric Glax. I'm going to do a little bit about that in the next topic, but that's a really good book if you want to hear about a lot of that data and many other things. Actually, I'd recommend the entire book. I'm going to put the sources for the things I use today. I'm going to try to put the sources in the show notes. But we're going to move on to our next topic, which actually is smoking and cancer, because I think it's all well and good me talking about nuclear disasters and all the rest of it, and I could do that, but I think the problem with me doing that is, number one, I think there's a large amount of data on that already, and second of all, I just think that realistically, that stuff, people focus on the really stuff that's going to kill you in those instances or really cause damage, but I think what people don't realize is that day to day, there's a lot more going on as well with radiation, because it's literally everywhere. And I mean, every year you are going to take in, depending where you live and who you are and what you do, you're going to take in 3 millisieverts of radiation per year. And there's nothing you can do about that. That's just the reality of living. If you live in something like Denver, I think it's 7. I think if you're an airline crew, obviously you're closer to the sun, so you're going to take more in. But I just want to go on this topic of smoking and cancer, because for the simple reason, it's just an everyday thing that people don't realize actually is quite radioactive. So we'll start with that. I'm reading directly from the book that I mentioned earlier, which is, one way smoking cigarettes causes cancer is by delivering radioactive materials into the lungs. Smoking cigarettes puts the smoker at risk for 5 of the most common causes of death worldwide, including heart and vascular diseases, cancer, emphysema, and pneumonia. Worse yet, sudden infant death syndrome and premature births are more common in the children of smokers. There are 5.4 million tobacco-related deaths worldwide each year, 1.3 million of them from lung cancer. Approximately 443,000 Americans die each year from tobacco-related illnesses. About 50,000 of them are non-smokers killed by the effects of secondhand smoke. The number of non-smokers killed worldwide is about 600,000. On average, smokers live about 13 years less than comparable non-smokers. 8 out of every 10 lung cancer deaths are caused by smoking. Yet 130 years ago, a physician who discovered lung cancer in someone would have found the condition so rare that it wouldn't have been worth reporting in the medical literature. By 1889, only 140 cases of lung cancer were reported worldwide. The first edition of the widely used Merck manual, published that year, listed cigarette smoking as a possible treatment for bronchitis and asthma. He just prescribed you 20 cigarettes to, keep the asthma at bay. Why not? It took until 1912, which, if my maths is any good, 22, which is 23 years later, for someone to suggest that smoking caused lung cancer. And that was to just suggest it, not proven by that point. What happened? According to the World Health Organization International Agency for Research on Cancer, tobacco smoke is approximately 5% tar and 95% gas, containing more than 4,000 chemically distinct compounds. At least 60 of these are known to cause cancer in animals. 11 cause cancer in humans, including arsenic, benzene, radium-222, and thorium. In a word, however, what made smoking even unhealthier is not what is in the tobacco, but what is on it: fertilizer. I find this next part, I wouldn't say quite shocking, but it's unbelievable. You wouldn't really believe this. So, fertilizers used in growing tobacco and many other plants are rich in chemicals, including radium-226. The number 226 is, as we talked about earlier, that's the isotope, which means it's a radioactive isotope. And its decay products, including polonium-210. Anything grown where there is uranium-238 in the ground or with the aid of these fertilizers picks up radionuclides from uranium-238 decay products, including radium-226, which gathers in their leaves as with spinach or broccoli. This is not necessarily dangerous. About 3/4 of the polonium-210 that enters our body comes from our food, and 50 to 90% of it is excreted in our sweat and feces. The remainder, however, stays in the body and circulates via the blood throughout the body. Cigarette smokers have 30% more polonium-210 in their blood than non-smokers. When someone lights a cigarette and draws in the smoke, the temperature of the tobacco in the middle of the red ember is about 1,500 degrees Fahrenheit, or, for everyone else not in the US, 800 to 900 degrees Celsius. This aerosolizes the polonium-210, which is then inhaled directly into the bronchial tree and lungs. Filters are of little help. They reduce inhaled polonium-210 levels by less than 5%. Polonium-210 in the leaves of, say, spinach or broccoli is not dangerous, unless for some reason you choose to smoke them and aerosolize it. But smoking a cigarette is, in some regards, like intentionally inhaling a small nuclear weapon into your lungs. Cigarette manufacturers have known about the presence of polonium-210 in tobacco since the 1960s. Polonium-210 in the wrong part of the body can be deadly in even the smallest amount. It is 250,000 times more toxic than cyanide. A lethal dose of polonium-210 weighs 0.1 milligram, a tenth of a millionth of a gram, or less than a millionth of the weight of a snowflake. It has been used at least once as a murder weapon. In November 2006, Alexander Litvenko, a former officer in the Federal Security Service of the Russian Federation, FSB, the successor of the KGB, then living in London, who claimed in 2 books that Vladimir Putin's rise to power was organized by the FSB, fell mysteriously ill and died 3 weeks later. An autopsy showed acute radiation poisoning from polonium-210, which was traced to a Russian nuclear power facility and thence to 2 FSB agents who handled it before surreptitiously slipping it into Litvenko's food at a London sushi restaurant. So, I mean, there's more there, but ultimately, the thing that you're actually smoking was used as a murder weapon, and it's crazy that on the warnings for cigarettes they put all kinds of things, and they say you'll get lung cancer, you say this, and I think people laugh off, and fair enough. But they don't have put on there, these are literally radioactive when you smoke them, and you're inhaling it directly into your lungs. If you put that on it, I think people would, they would think a little bit more, I think, because radiation has that effect, doesn't it? And I mean, 8 out of 10 of lung cancers is literally caused by smoking. And the survival rate on lung cancer, I have to tell everybody, is not great. Usually because if you smoke, you're coughing a lot anyway, you're probably not going to realize till blood starts coming out or something like that. Now, if you smoke, that's completely up to you. I smoked before as well, and no sort of judgment on this. I just feel like it's fair that everybody has the same information on these things, because I only learnt this fact a little while ago, and it blew me away a little bit, because, well, you don't, because you know why it happens, but you don't know why it happens. And that's really the sort of, I suppose, subatomic level of what's going on. And yeah, I just think it's really interesting. There's more topics that I can do in such a things areas as medical, for CT scans and things like that. And maybe I'll be able to fit it a little bit in the end. But what I really want to move on to now is nuclear power, for the simple reason I think that it's a source of energy that I think people don't really understand. And maybe if we learnt more about it, we'd actually be more positive towards nuclear fission. So I want to start off by saying I think it's great that we have sources of green energy such as water and wind and solar and things like that. And I'm really behind that. But to be honest, having looked at some of the energy required and any energy production from such things, I think that we have to get real. That's going to be a supplement to the grid, but it's not going to be the driving force. Now, I just want to look at a country such as France, which has made 80% of its energy production as nuclear power. That they've built that many nuclear power plants. In fact, they've built so much of it, they're actually exporting it to places like United Kingdom, which haven't built enough nuclear power stations in the last 20 to 30 years, which I think is absolutely crazy that, well, the United Kingdom hasn't done that. I think we have to understand, first of all, why people don't trust it and why there's almost a hysteria to nuclear power. So we have to go to Chernobyl and Fukushima, which is the two most widely known nuclear disasters. But I think that people don't really understand why they happened. They know they happened, and they know the human story, especially behind Chernobyl. And fair enough, it's very compelling, and there's all kinds of things that get caught up in there. But I don't think many people mainly try to understand the reasons behind a nuclear reactor actually what that had, which wasn't a nuclear explosion. It was a pressure explosion, likely from the water and hydrogen and steam. However, I have to tell you now that a modern PWR reactor, or any kind of reactor that I'm aware of, is not built the same as an RBMK reactor. I think is it RMBK? RBMK? Either way, it's not built the same as that reactor. It doesn't have reactors today, don't have modern PWR reactors, which is water reactors, don't have a positive void coefficient. I won't get into the details of that too much, but what that essentially means is that when you raise power inside of the reactor, the more you do that, the less reactive the water reactors become. Now, with the old Russian reactor from Chernobyl, it was the opposite, and they knew they had this problem, and I'll get into that in a little bit. But essentially, their reactor, the more you raise reactivity, the more power, and the more it would go up. It had a positive reaction. You don't have that in other reactors, and they knew about this problem in the USSR. In fact, Reactor 1 had a partial meltdown some years before. Reactor 4, which was the one that exploded, literally failed all of its safety tests on the years lining up to the event. But they couldn't turn off the power because the biggest city in Ukraine would have no energy, no power. And they couldn't do it because they're all living in the illusion that the USSR was still working when it was a total failure, especially by that point. So what they did was they lived in this illusion where they said literally that it could never explode and there's nothing wrong with it and they can essentially do whatever they like. And the stupid operators, and I have to say that, especially the leader, basically caused a massive pressure explosion inside the reactor from sheer stupidity. There's reasons behind that and scientific reasons, which I'm not going to go into because I'm trying to keep it in 30 minutes and I'm probably not going to do it. But that will not happen again. And at least in this country, anyway, in the UK and the US especially uses PWR reactors. So that won't happen. And you might say, well, other things will happen. Okay, so let's look at Fukushima. Fukushima was a natural disaster. It had a tsunami that went over the 4-foot wall they built, their seawall that they built, and it flooded the reactors. Now, what happens there is that its connection to the grid and therefore your ability to control what the reactors are doing and shutting them off and so on is gone. However, what is meant to happen is you're meant to have a diesel generator, which then kicks in and gives you power, despite the fact that the electricity grid has gone down in that area. However, in their foresight, they decided, as luck and irony would have it, to put those diesel generators in the basement, where they proceeded to also flood. So there's two things that went wrong in that situation. They didn't build a high enough seawall because there was a 10-foot, or I think it was a 10-foot, 11-foot wave that came over, much higher than the wall that they built. And they put the diesel generators in probably the stupidest place, let's be honest. So was it avoidable? I mean, both disasters were avoidable. In Chernobyl, it was a complete disaster. In Fukushima, it wasn't a complete disaster. I haven't heard of anyone dying. What's happened? A lot of it was pumped back into the sea. And actually, contrary to what people believe, there's been a lot of nuclear dumping in the sea for many decades, and it doesn't actually do as much as you would expect because it dilutes it so much that it really doesn't do as much as you might imagine. I'm not saying it's a great thing and it's what we should be doing, but what happened in Chernobyl, it was released over land into the air and caused problems in the rest of Europe. In Fukushima, it all went into the sea or went over the Pacific Ocean and didn't cause a great deal of damage. So, yeah, what's happening today with Fukushima, my understanding of it is there's still cesium, radioactive cesium coming out the top. That's been looked at, and I don't think it's causing a lot of problems. But the statistics still haven't come back to how many cancer over the long term, how many cancer cases that's actually caused. I guess we'll find out. The point is, both disasters have a lot of hysteria, but there are actually very reasonable ways that it could have been completely avoided. And from all the hundreds of nuclear reactors that exist and have existed to disasters, I think it's not amazing, I suppose, if you look at those kind of odds, but in the early years of these things, I don't think it's necessarily too bad. But maybe you disagree with me, and that's completely fair enough. But what I say is we have to get real. And going back to the fact that France has 80% of its power, and so much so that it's been able to export power, we have to point out that uranium is free and abundant all over this planet, and there's lots of it. And it's incredibly powerful when we put it into nuclear fission. And it releases a lot of energy, and it's the kind of energy we are going to need when we're going into such an advanced civilization with AI, with all kinds of power sort of things that are coming. I mean, how many gadgets have LEDs? How many gadgets have so many different lights now? So many more computers, so many everything, electric cars. We are going to need a form of energy which is able to produce incredible output. And there we are looking at, I mean, you can build lots of solar farms and it can take up lots of land and fine, but you could build one nuclear site and have 4 to 5 reactors on it, and that would be all you needed in one place. Now, a lot of people, there's two things that people also get worried about, which is nuclear waste. And I have to say that nuclear waste isn't it is a problem, and it is a problem that has to be overcome. However, I'll just get you through a little bit of what happens with nuclear uranium, which is depleted. Some of it is taken out of the fuel rods and it can be reused. Some of it goes and is buried in places that you've heard about. But in the US statistic is that I think that you could take all of their depleted uranium from the last however many decades and fit it into one football field. I think the football field would have some depth to it. I think that's the way of my understanding of that fact. But considering how long they've all been running and how many they have, and I can't remember how many they have, but that's not as much as you think it was. When you think of waste, you think of general waste, you think of landfills everywhere, but that's lots of people with lots of things. We're talking about a few hundred sites in a few places. And actually, it ultimately doesn't take up as much space and cause as much waste as you think. And there are ways of reprocessing that uranium. I can't remember the exact way of doing it, but they basically fission it off to create plutonium, and that plutonium can then be recycled, and there's a certain kind of reactor that's able to do it. But plutonium is controversial, obviously, because it can go into nuclear bombs and nuclear weapons. But nuclear weapons are an unfortunate reality of an advanced form of energy. It was always going to happen. It has always happened in human history. When there's ever been a new great scientific invention, there's always some person who comes out and turns it into a weapon. And I know it's a different ball game because we're talking about world-ending weapons now, and I completely understand that. But there are ways to reprocess the waste. The problem is people like the countries like the US and so on have made reprocessing it illegal, and they all have their very own reasons for it, and it does cause radiation to an extent. But ultimately, I want people to look into the case of nuclear power a bit more. A good book, actually, is How to Drive a Nuclear Reactor by Colin Tucker. That's a really good book. Less so about the political side of it, and more so it teaches you how a nuclear reactor works, how much energy it's going to produce, things like that. And actually, it's really good. He's worked in the industry for, my understanding, is many years. And if you're interested in that, I'll put the link to that book in the show notes, as well as the other book. And that's more I want to say about nuclear power. I could say more, but I don't want to take up everyone's time on this. And I just end this actually with, there's a few obscure things that maybe I could bring up. And I think that, yeah, so there's a few maybe obscure facts that, well, this one actually about space was really interesting. So, do astronauts and cosmonauts need to worry about radiation? Yes, a lot. Space travel involves many complex risks, one of which is exposure to the same ionizing radiations we are exposed to on Earth, mostly X-rays and gamma rays from photons that make it through our atmosphere. However, similar to people living in Denver and airline flight crews who receive more background radiation than most of us because they are closer to the sun, astronauts, such as those living on the International Space Station, ISS, receive a higher radiation dose. For example, a 6 months residence in the ISS results in a dose of about 120 millisieverts, or about 1/2 of the dose of the average atomic bomb survivor. This is about 60 times more than they would receive if they remained on Earth. Cosmonauts on long space missions, especially interplanetary travel, will receive much higher doses. For example, persons going to, and hopefully returning from a trip to Mars, might receive a dose of 1,000 millisieverts, or 5 times as much as the average atomic bomb survivor. There are 3 sources of radiation cosmonauts will be exposed to. Number 1, solar particle events coming from our sun, which occur episodically, vary with the solar cycle. Solar flare and coronal mass ejections can only be partially predicted. Number 2, galactic cosmic events coming from the galaxy exclusive of our sun, which are high-energy charged atoms stripped of their electrons, travelling near the speed of light and able to penetrate almost anything. And 3, radiation belts trapped by the Earth's magnetic field. Moreover, although scientists have a reasonably good idea about the potential health consequences of some types of radiation cosmonauts will be exposed to, such as gamma rays and protons, very little is known about the potential health effects of charged ions heavier than hydrogen, which makes up protons. So, NASA and other such space agencies are looking into how they're going to come up with radiation shielding, even for just a trip to Mars, but potentially getting 1,000 millisieverts. I think my understanding of that is it would be fatal, right? So we think about how we're going to get there and land there and build the ship, do it. But actually, maybe the hardest part is overcoming the radiation. So how are we going to create shielding? We're going to need maybe more advanced energy to be able to do that as well. So the future we're going into is going to require a lot of pull and a lot of energy from places. So this kind of radiation, other things, is something that's going to become more of a reality, I think, as the future goes on and on and on. So that's the obscure fact about space. I think I just want to end it on the fact that airline pilots receive more radiation as well. If you get a CT scan, you get 25 millisieverts just from one scan. Bear in mind, you get 3 millisieverts per year just by living. Now, 25 millisieverts. I mean, you'd have to live however many years to just from one scan. So if your doctor is giving you lots of scans, maybe question it, because, well, I'm sure they outweigh the risks. You want to make sure they are outweighing the risks, because there are risks, and your risk of cancer can go up, and that's something that you need to keep in mind. If you're a man, you're more likely to get cancer than women. I think my understanding of the data is that men their radiation dose is like 45%. I think they're 45% likely to get cancer. That could be wrong. I don't know if it's cancer. I think women, it's about 37. It's mainly because of their size. If you're bigger, your risk of taking radiation is higher, because of, I suppose, there's more of you to take it in, I guess, and the heat, I suppose, you would produce, perhaps. So yeah, just keep yourself safe out there. There's other things that I would like to get into, such as skin cancers. It's a very cheerful episode, isn't it? Such as skin cancers and other things such as that, and keeping yourself safe in the sun. But I think I can sum that up in the fact that suntan will keep you safe. Sunscreen will keep you safe from all skin cancers except melanoma. Don't spend too much time in the sunbed. Don't spend too much more time in the sun than you need to, especially if you've got pale skin, because you cannot protect your skin from melanoma even with sunscreen. So be very careful with that. If you have darker skin and perhaps you're black, I think you're much less likely to get things like that. But also keep in mind that your ability to take in the sun lowers your vitamin D intake. So if you live in an overcast country and you are black, perhaps think about supplementing vitamin D. I'm not a doctor. Dr. Onan's in this week. However, I just wanted things that I've been looking into for over the last however long that I've been doing it. And I think it's interesting. And I think it's important that people know this stuff so they can make up the best decent decisions for themselves. Or maybe they just don't care. Maybe you want to live the life the way you want to live. And you know what? That's fine. It's completely up to you. There's absolutely nothing that affects anyone else except for maybe smoking, maybe go outside and, well, maybe, because I think that one can be quite damaging, I guess. But maybe I've said enough today. Maybe, they say, Mr. Red, you're talking too much. You just need to be quiet. So that's fine. I'm completely on board with that, because I've just gone over. I'm on about 32 minutes, 33 minutes. So I've just gone over. But you know what? There it is. There's radiation. I've been wanting to get out for a while. Everyone around me knows I've been wanting to get out for a while. Now I have. Maybe I'll feel better. I'll put the sources that I've read from in the show notes. And thanks very much for listening to this bonus episode. I hope you found it informative. Can we go that far with this show that it's actually informative? I don't know. Anyway, thanks very much. Thanks for joining in. There'll be a new episode coming soon, and we will see you there, or hear you there, or you'll hear us, whatever. Goodbye.
Mission 31D, the first flight of the orbital Discovery, and the shuttle has cleared the tower.
One philosopher asserted that he knew the whole secret.
Welcome home, folks. Beautiful. Furthermore, it reads, he is equal and he is square, in which energy is but equal to mass.
After serving the world for over 30 years, space haven't turned its back on history. It's come to a final stop. Apollo 10, Houston, 2 minutes to LOS. Everybody here says Godspeed. Okay, and we'll see you right on the other side in orbit.